Hello everyone. In this video, you are going to learn how to derive one-dimensional wave equation in the form dou square u by dou t square equal to c square times dou square u by dou x square. Okay. First, let us consider a straightly stretched elastic string of length L, which is fixed at the ends A and B. Okay. Tightly stretched elastic string of length L, which is fixed at A and B and which is subjected to constant tension, capital T. And also the tension T will be considered to be a large compared to the weight of the string. Since weight of the string, when comparing, the tension capital T generated on the spring is very large. So that the effect of gravity, that is gravitational acceleration, is neglected. Okay. Let the string is released from the rest and allowed to vibrate. Allowed to vibrate vertically. Assume the vibrating of the string is entirely in one plane. Means it is in x and y plane. It's better to convert this y in terms of u axis. So that you will get dou u by dou square u by dou t square and dou square u by dou x square. So this is my x axis and this is my u axis. Now, taking the end A as origin, and AB is the x axis and AU is the y axis, or you can refer it as u axis. Now, the motion takes place entirely in the xy plane, I mean this plane. Consider the motion of the element PQ. Before that, I will take a small portion of this wire P and Q. Okay, small portion of this wire P and Q. Okay, and I will draw the tangents at P, T1. T is the tension generated on the spring, and at Q also I will draw a tangent capital T. And here the angle between the tangent at P with the horizontal is xi. Okay, and angle between the tangent at Q and the horizontal is xi plus delta xi. Okay, and this is the x reference. I mean P is at distance x comma y and Q is at the distance x plus delta x comma y plus delta y. So this distance is x, this distance is x plus delta x. So the distance between P and Q is delta x. Okay. Similarly, this distance is y, this distance is y plus delta y. So the distance between P and Q is delta x here. Okay, in horizontal xy plane. Now consider the motion of the element PQ of the string between P and Q. At the point P and Q, we are considering a smallest portion of the string and considering the motion between this element PQ. Okay, where the tangents makes an angle xi and delta xi. The angle xi at P and xi plus delta xi at Q with the x-axis or horizontal axis. Clearly, the element is moving upward with the acceleration dou square u by dou t square. Okay, the acceleration is equal to dou square u by dou x square, which is vertically upwards. Now, vertical component of the force acting on this element PQ. Okay, the vertical component of the force, I mean the tension, which is T times sine of xi plus delta xi at Q. Okay, at this point, the vertical component of the force is tension times sine of xi plus delta xi minus at this point at P, the vertical component of the force is T times sine of Z, sine of the angle between the tangent with the horizontal at P. Next, T is common, you can take out. Since Xi is very small, you can consider sine of Xi is nearly equal to tan Xi. That's nothing but 0. It's nearly equal to 0. So I will convert this sine trigonometric function in terms of tangent, tan of Xi and tan of Xi plus delta Xi respectively. Next, we know that slope of the tangent is always, slope of the tangent is nothing but tan of Xi or tan of Xi plus delta Xi, which is equal to differentiation of u with respect to x. Correct? Differentiation of u with respect to x here partially. Okay, dou u by dou x. Here also dou u by dou x at q. So the point here it is x plus delta x, and this dou u by dou x is the slope of this tangent, is dou u by dou x at the point P. That's nothing but x. Next, let us consider m is the mass per unit length of the string. Then by Newton's second law of motion, that is F is equal to ma. By using this Newton's second law of motion, we have mass of the string is m, mass per unit length of the string is m. So mass of the string is m times the length, m times the length is delta x of the element pq. Pq length is nothing but delta x. So mass into the length gives the total mass, correct? Mass per unit length into the length times dou square u by dou t square is equal to T times the same quantity. You can write that's the force, vertical component of the force. Next, dividing by m and delta x throughout this equation, so that you will get dou square u by dou t square is equal to T divided by m into dou u by dou x at the point x plus delta x minus dou u by dou x at the point x whole divided by this delta x. Next, taking the limit whenever q reaches to q p, the element q whenever near to q p, then the value of delta x near to 0, right? The distance between p and q is nearly equal to 0. So delta x tends to 0. That case, you will get dou square u by dou t square. Here, dou square u by dou t square is equal to t and m are constant. While taking limit delta x tends to 0, the whole quantity of this term, that is dou u by dou x at the point x plus delta x minus dou u by dou x at the point x whole divided by delta x, by using the definition of limit, that is definition of derivative, limit definition of partial derivatives, which is equal to dou by dou x of dou u by dou x. Or you can write t by m as some constant c square, okay, and it is dou square u by dou x square, by using the limit definition of the differentiation. Now, dou square u by dou t square equal to c square times dou square u by dou x square, and this is called as, this equation is called as transverse vibration of the string, or also called as one-dimensional wave equation. Wave equation in one dimension. In the next video, I'm going to explain or derive the one-dimensional heat equation ut equal to c square uxx.